Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on November 25th, 2025, about 5 days ago. It introduces a verification scheme that can catch 4-bit model quantization with AUC above 0.999, using at most 300 output tokens, and in its activation-based version does the same using just 2 tokens while cutting communication by roughly 25 to 75%. The paper is titled DiFR, Inference Verification Despite Non-Determinism. And as we will see later, the approach makes trustworthy large model inference feel surprisingly practical. Alright, Figure 1 shows how well the token DiFR score separates correct runs from misconfigured ones as the verifier aggregates more tokens. The left set of plots covers the Llama 3.18 billion model and reaches near perfect detection for all 4 bug types within a few thousand tokens. On the right, the QN 330 billion model still shows strong detection for big errors, but a tiny temperature change is harder because hardware differences add benign noise. Overall, token DiFR consistently outperforms cross-entropy, especially for quantization and seed mistakes. So while Figure 1 showed baseline misconfigurations, Figure 2 tests an explicit attack that tries to fool the detector. The attacker tweaks the sampling temperature, so the misconfigured quantized model has the same mean cross-entropy as the reference. Cross-entropy curves in red stay stuck near chance across all batch sizes, which means they fail completely. The blue token DiFR curves instead climb sharply toward near-perfect AUC as the token batch grows, so the method resists this simple adversarial manipulation. Well, Figure 3 turns to random sampling bugs, where the system sometimes ignores logits and just picks from the top K tokens. The 4 panels plot detection AUC as batch size grows for K equals 2 and K equals 32 on 2 different models. For Llama 3.18 billion, token DiFR quickly outpaces cross-entropy and reaches near-perfect detection. For the noisier QN 330 billion model, the mean pooled token DiFR metric struggles on the rare K equals 2 bug, which motivates smarter tail-focused pooling later. Alright, Figure 4 shifts from token scores to activation fingerprints and compares activation DiFR against TopLock. The 4 panels show AUC versus batch size for key-value cache versus full model quantization on 2 models. Activation DiFR in blue climbs to near-perfect detection using only a few tokens, especially for the smaller Llama model. At matched projection dimension, the blue curves consistently sit above or equal to the red TopLock curves, so activation DiFR delivers stronger detection for the same communication cost. So while Figure 4 compared accuracy versus batch size, Table 1 turns that into concrete communication cost. The table reports how many bytes per token each method needs to hit several AUC targets when detecting key-value cache quantization. Across all 3 model and hardware setups, activation DiFR consistently uses fewer bytes per token than TopLock for the same accuracy. In the hardest QN 30 billion A100 case, activation DiFR reaches near perfect AUC with roughly a quarter of the bandwidth that TopLock requires. So while Table 1 summarized specific cost points, Figure 7 shows the full Pareto frontier of accuracy versus communication cost. The left and right panels plot best AUC at 1% false positive rate against bytes per token for 2 8 billion parameter models. Blue activation DiFR curves always reach a given accuracy at lower or equal cost than the red TopLock curves, which means activation fingerprints from DiFR are strictly more communication efficient across this task. Token DiFR and activation DiFR together show that trustworthy verification of large model inference is actually practical, even when hardware noise makes exact replay impossible. The work suggests a path toward routine auditing of open-weight model providers, with low overhead and strong detection of misconfigurations and tampering. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.